Mouse button not working. Yeah. We're going to finish up. Actually, David came back. I got the wrong one. Now we're going to finish up the rest of practical circuits. I think there's 3 or 4 of those. So we're going to talk about reactance modulators and balanced modulators. The circuits are used for detection of AM and FM and mixers. So modulation is just the process of adding information to some form of carrier signal. I guess the first one was Morse code. You turn the carrier on and off. Then we started doing voice modulation. The AM mode, I think, was probably the first, where we use a voice signal to modulate the carrier amplitude, change the amplitude of the carrier. And then came about frequency modulation, where instead of changing the amplitude, you change the frequency of the carrier based on the amplitude and frequency of the modulating signal. Then came single sideband, which is just a special case of amplitude modulation. The difference is you only transmit one sideband of the audio and suppress the carrier. Whereas in normal amplitude modulation, you still have the carrier signal, and then you have the baseband or modulating signal mirrored on either side of it. So you have an upper and a lower. We call those upper and lower sidebands. In the case of single sideband, you essentially eliminate or filter out the carrier at one of the bands, which lets you put all the power into a smaller bandwidth. So you don't have any power generating the carrier or say the lower sideband if you're running upper sideband. So it's a lot more efficient, which is why it's basically used in amateur radio for voice communications. Not too many people actually do AM, where FM is still predominant on the higher frequencies, or 2 meters, 70 centimeters, and up. There's also a variation of FM, which is called phase modulation, where you change the phase of the signal. In other words, you're changing it less than cycles, just a portion of the cycle. And that's called phase modulation. Turns out the same circuitry can kind of be used to do either, and the detection is essentially the same. And from what I understand, a human can't tell the difference between a signal that's phase modulated or frequency modulated in reception.
It's one harder to do than the other. So I'm thinking the higher your frequency is to phase.
A lot of the digital modes, in fact, I'd say majority of the digital modes use phase modulation or audio frequency. keying, shift keying. And like I said, this requires a modulator that either allows you to vary the phase or the frequency of the signal. We call those reactance modulators. That's important because there's a question about what's it called, I believe. Normally it's done by using a varactor, which we talked about earlier, of a voltage variable capacitor, where you take advantage of the varying depletion zone depending on how you bias it to change the effective capacitance. It looks like a capacitor instead of a diode because it's reverse biased. And for those people that really like math, there's all the equations for phase and frequency modulation down there. You don't have to know those. There's just a picture down on the bottom left of what frequency modulation kind of looks like, with the carrier frequency changing in proportion to the amplitude of the modulating signal. So you can see as the modulating signal goes positive, you're increasing the frequency, and as it goes negative, you're decreasing frequency. If you look at it in the frequency domain by doing a Fourier transform, which we'll talk about a little bit later, you can see, and this was, I believe it was a 10 kilohertz carrier and a 1 kilohertz modulating signal. And you can see what the spectrum looks like, where the carrier is here at, excuse me, not kilohertz, megahertz. And you can see the harmonics of the modulating signal as the signal deviates. And in this case, you're seeing both sidebands, even on FM. This is what a typical varactor diode modulator looks like, where you're using that to change the capacitance of the resonant circuit there on the oscillator. And it has that blocking capacitor, and it's fed with a negative DC bias, so the diode is reverse biased, so you can use it as a variable capacitor. So which of the following can be used to generate FM phone signals? Any more bravos? 2 bravos. Bravo sounds like a winner. Whoops.
Yeah, you got sandwich.
I'm having trouble. All right. I need a battery. Also at FM, they tend to use what's called a pre-emphasis network, which will shift the modulating signal up to the higher end. It just seems to make it work better as far as detection. And obviously on the opposite end, they have a de-emphasis network, which kind of undoes the pre-emphasis. And one of the things that they use that for is so it's compatible if you're using phase modulation as opposed to pure frequency modulation. This is some typical what the pre-emphasis circuit looks like, and if you really recognize this, it's a high-pass filter. And the de-emphasis is just a low-pass filter. And they're set for a particular frequency that's in the baseband range. So what is added to an FM speech channel to boost the higher audio frequencies? You're guessing? What's going on with this mouse? Why is de-emphasis commonly used in FM communication receivers?
It's a finance page. Down.
Well, go ahead.
It's your frequency. If your frequency, you're doing phase one, takes reasonable frequency to be able.
Honestly, I can't tell you the subtleties between phase and frequency modulation. But apparently, the higher frequencies have an effect on phase modulation more than they do on the frequency modulation. But as I recall, all TV, or at least in the old days, before everything was digital, always used pre-emphasis and de-emphasis on the audio channel, which was FM. So alpha, damn. So to generate AM, okay, we basically use a mixer circuit. And what it kind of does a cross product two frequencies. So you wind up getting the two input frequencies, your carrier and your modulating frequency, which we call baseband, and the sum of difference as the outputs. So you get 4 out, 2 in, 4 out. And that's what I just said. Now, if you, we got. If you overmodulate, then you'll tend to start getting spurs, frequency spurs. It's sort of an intermodulation product. We're showing here the carrier being modulated, and actually you have to offset the baseband signal so it's varying DC. If you actually were to do it with a pure alternating positive negative, you get a double sidebands. Kind of looks like a distortion. So you can see that the modulating signal is going from 0 up to 6 volts in this case. And spectrum, where you see the carrier and then you see the 2 sidebands. Now they're just very narrow because it's a fixed frequency that we're modulating with. If that was voice, it would be that whole audio spectrum that you're modulating. And again, for the math people, there's the math to derive it. We talked about baseband, and it's that frequency range that typically your voice. In the digital, it could be generated tones. It turns out that there's also this imaginary negative frequency that we don't really deal with because it's imaginary. But you do have, in the case of the carrier, you've got a positive and a negative carrier. So when you modulate it, you get sidebands. You got the carrier over here and the sidebands on either side, and then you have a imaginary duplicate down there too. This is just showing where you're, when you modulate it, the fundamental frequency, and then if you're
Hello, hello.
Hello. Who's speaking? Hello? Can you hear me? Okay. Now this is showing where the spurs may pop up, and it's, you know, it's not an even harmonic of the signals. It depends on the difference in frequencies that it's seeing. So it's really intermodulation, where you get the 2F minus F1 and so forth. We'll talk about in a little bit. I'm not sure how to fix my mouse. Okay, what's meant by the term baseband? Yeah, it's band frequencies.
Yes.
Get to be on stage.
Yes, they.
That's what goes in.
Bravo.
I'm just having a hard time understanding all this. Everybody else. Makes sense to me.
Yeah, you're just stuck. Yeah, look, seriously, this is all this is deep stuff. But I'm
Well, ask questions.
just sorting.
So,
We just call it baseband because that's the lower frequency you're modulating with.
You go back. Slide.
Yeah, even if I don't want to. That one? Come on.
Can you just hit your back key on your keyboard? Left and right key.
Yeah, maybe that'll work.
Alright, so bass, that's left thing right there, right? And then
See, that's your voice.
that's what your microphone
And that-
radio hears from, like.
That 0 is 0 hertz.
oh,
And you're going up to, in the case of normal voice, around 3 kilohertz.
And then the radio, once it does these.
Which is over on the right. In the middle is the carrier. Okay. See, that's just single, because it's a fixed frequency. Okay, that's your 14.0 whatever you're transmitting.
so it's just a number.
Right. That's the variable frequency oscillator in your radio, in your transmitter. When you mix the baseband with the carrier, you get a waveform that looks like on the right. Okay, so forget about the ones on the left because they're imaginary, but mathematically they're there. So you see the center is the carrier where that little mark is, and then you have whatever your baseband was on either side of it. So it'd be like plus and minus 3 kilohertz case on either side of the carrier. That's AM, standard AM, or double sideband. Usually double sideband, they suppress the carrier, so you only see the sidebands.
I see.
When we do single sideband, we get rid of one of the sidebands and the carrier. So you just see the baseband signal shifted in frequency up there where next to where the carrier should be.
So if you, and the reason we do this, you look at basebands. If you look at the whole area under the curve, like that space, there's a lot of space there. So you have finite amount of occasion to transmit. And you're putting it all towards amplifier all at once. So and radio radios instead, we can use one of those two in that graph on the right. If you're 40 meters or lower, typically lowers. So everything above that left is just expressed, and the amplifier is younger with trying to by that seems get way more back. So we have to talk way further on the sleeping AM because AM is trying to power like full current,
Gotcha.
whereas sleeping.
So assume this is plus or minus 3 kilohertz. So it's 6 kilohertz bandwidth. You're putting out 100 watts. Okay. That's 100 watts divided by 6 kilohertz. Okay. So that's so many, whatever the math is, watts per hertz. If I do single sideband, I'm going to put 100 watts into that half. So I'm going to get twice as much power per hertz as I did with AM. Actually, even better than that because I don't do the carrier either.
Gotcha. Thank you very much.
Range.
No sideband is taking identical information. So you can strip off the right one, strip off the left one. It's substantially only me. Right. So
The difference is, and you notice, the one on the bottom, lower sideband, is inverted. What was the higher frequency on the baseband is the lower frequency. So that's something you have to take into account if you're listening to single sideband and it's on upper sideband and you are set up for lower sideband, it's going to sound kind of funky. Okay, so what is meant by baseband? Problem. The message signal. Doesn't have to be voice. What's the principal frequencies that appear at the output of a mixer circuit? Very good. I knew you weren't sleeping. There's two input frequencies and there's some and difference. So that's how you get the sidebands. It's sum and difference. So it'll be the carrier plus the sideband, the carrier minus the sideband.
So yeah, 14.1 megahertz carrying so 20 the mind stop. Hearing 14 original video 1000. You have 14,000 14 megahertz two. Right, one carrier, one megahertz. So box original wall, 2 megahertz, 2 that's which originally so
So what occurs if the input signals to a mixer are too high? It's spurious mixer products.
I counts to get the mic gain,
Yes.
which might be usually great players since you don't see how well against the green. We might be basically modulator drawing off the story go signal. So
It's very important in digital modes too. You have to set, usually it's called mic gain, which is part of the audio input or else on the computer. But you've got to set that audio level to a point where it's not overmodulating, because if it does, it brings the ALC on and it kind of distorts the signal. Okay, single sideband. Okay, is slightly different because we only want to transmit one of the sidebands. And we only want to detect that one sideband, which is harder than AM because you don't have a carrier frequency as a reference, which is why when you're tuning single sideband, as you change the frequency, you kind of get the rain barrel or the Donald Duck, because if you're not reproducing the same frequency range that the signal would generate it at because of that frequency shift. So you have to get it to where the carrier should have been in order to tune it properly. And you don't exactly know where the carrier should have been. Normally, to generate single sideband, we use a different type of mixer called a balanced mixer, or in some cases, a double balanced mixer. And the reason is it only generates the two sidebands, the sum and difference. You don't get the carrier out or the baseband out. You just get the two sidebands. So it already suppresses the carrier. So all you have to do is find a way to filter out the sideband that you don't want. This is kind of a circuit of a typical balanced modulator. This is done with a couple diodes. And you feed in the modulating signal in here and the carrier there, and it does a kind of a multiplication, but because it's balanced both sides, it cancels out the carrier from the baseband. What is one way a single sideband phone signal can be generated? It's not the only way. That's the way it used to be. When we talk about SDRs, it's a little different. Okay. So now that we've modulated signals, we have to demodulate them. So for an AM, we just use a simple diode detector, which is called an envelope detector, because all we're doing is rectifying the carrier and reproducing the envelope of it, the variations in amplitude. And that's our baseband signal. So we're essentially integrating the carrier and getting the baseband signal back. It's a fairly simple circuit. This is kind of a typical one, and you're feeding it into a little following amplifier to drive the output. So it's just essentially that diode and a capacitor. How does the diode envelope detector function? Can you go with alpha? Single sideband is different, which don't really have the envelope because they don't have a modulated carrier. All we have is baseband shifted in frequency. So we have to use what's called a product detector. And it's essentially a mixer and a filter where we're, again, mixing or doing the product of two signals. So we have a beat frequency oscillator and the modulated signal. And the output of that is going to give you the baseband signal back. So just so you say you've seen a product detector. So what type of detector circuit is used for demodulating single sideband signal? This is the test of your short-term memory. Okay, when we do FM, we need yet a different type of detector. And it's used to be called a discriminator or ratio detector. I can't honestly say I totally understand how the circuit works. It detects the change in frequency or phase and changes that to a varying amplitude. And there's a typical circuit, and I think the way it works is as the frequency changes, and somebody that knows, tell me if I'm right. The higher frequency charges these two capacitors up to a higher voltage because they have a certain time constant. So at the lowest frequency, it's going to have time to decay. So the higher the frequency, the more pulses I'm getting to charge it up. So I get a higher voltage. And somehow that upsets the little bridge there, and I can see that change in amplitude on the output or something like that. I won't guarantee it, but that's what I think it is. So what is a frequency discriminator? Come on, this is a hard one. Okay. Wasn't that fun?
That was students.